Good afternoon, everyone. Today we are going to show a general result, namely if f of x is defined in this way and then g of x defined in that way, we want to show that for all values of x, except when x equals 0, that serves as a non-permissible value, right? We have an x being in the denominator, right? That would make the denominator 0. Can't do that. But for all values of x other than 0, we want to show that this general result, that x times g of x minus g of 1 over x, that just means g of x with 1 over x replacing x everywhere that x pops into play, right? X times g of x minus g of 1 over x is equal to 0 always. So this is going to be an exercise in algebraic manipulation and going from the initial way that g of x is defined, incorporating f of x into it, and then finally, slowly, step by step, getting down to show our desired result. Okay. So first of all, we know what f of x is. Let's plug f of x into g of x and see if we can simplify that down. Okay. So we have that g of x is defined to be the log base 2 of f of x over 1 minus f of x. F of x is this quotient, and so let's write that as 2 to the power of 1 over x plus 1 over 1 plus 2 to the power of 1 over x plus 1 all over 1 minus all that. And so that means 1 minus 2 to the power of 1 over x plus 1 over 1 plus 2 to the power of 1 over x plus 1, right? All I'm doing is writing the expression for f of x into g of x. And now we're going to hope to simplify this down using some nice algebraic techniques, okay? The first thing that comes to mind when I look at this expression is this 1 in the bottom, in the denominator here. We're subtracting a fraction from a whole number, right? Ever since we've been very little, we've known that to subtract fractions from anything, we need common denominators, right? And so what that means is we can rewrite this 1 as this denominator over itself, right? The same way we always have. And so we can write this 1 as 1 plus 2 to the power of 1 over x plus 1 over itself to 1 plus 2 to the power of 1 over x plus 1, right? That means that now we have a common denominator, and so we'll be able to actually subtract the numerators, right? And so now we can write a version of g of x that looks like the log base 2 of, let's simplify this down a bit, 2 to the power of 1 over x plus 1 over 1 plus 2 to the power of 1 over x plus 1 all over. Now that we have our common denominators, right, we can subtract the numerators. And so you'll notice that 1 plus 2 to the 1 over x plus 1 minus 2 to the 1 over x plus 1 means that the 2 to the power of 1 over x plus 1s completely cancel each other out. And so now all we have left in the numerator is 1, right? And so this quotient in the denominator of the entire expression is 1 over 1 plus 2 to the power of 1 over x plus 1, right? And at this point, you might observe that these two denominators are one and the same, right? They are identical. And so you've known for a long time now that when we have a quotient divided by a quotient, we can flip and multiply, as you've probably heard it called. And so let's go ahead and do that. G of x is the log base 2 of 2 to the power of 1 over x plus 1 over 1 plus 2 to the power of 1 over x plus 1 times, let's flip the bottom quotient, right? 1 plus 2 to the power of 1 over x plus 1 over 1. And then, in a convenient way, these two expressions completely cancel out, right, through multiplication. And so all we have left inside these brackets are 2 to the 1 over x plus 1 over 1. Over 1 does nothing. And so that means that we have a very simplified expression for g of x that is the log base 2 of simply 2 to the power of 1 over x plus 1, right? And now if you've been studying logarithms, you've known of a certain logarithm law, the power law, that says that if you have an exponent on the argument of a log, you can bounce it out front as a coefficient of that logarithm. And so that means that we can rewrite this logarithm as 1 over x plus 1 in front times the the log base 2 of 2. And we know that the log base 2 of 2 is equal to 1. And so this is 1 over x plus 1 times 1. And that means that this expression dwindles all the way down to 1 over x plus 1. And so let's box that in. That means that we've managed to simplify g of x from this daunting looking expression all the way down to little old 1 over x plus 1. This is our simplified expression for g of x. That's a really important result because with this very simplified version of g of x, finding an expression for g of 1 over x, which simply means where g of x is 1 over x plus 1, we're going to replace x in g of x. That means everywhere that x comes up in the expression for g of x, we're going to replace that x with 1 over x, right? Everywhere that x comes up, we replace x with 1 over x. The only place that it comes up is right there in that denominator. And so that means that we can find an expression for g of 1 over x without too much effort, because we're just going to plug in 1 over x in the only place that x comes up in the expression for g of x. And so g of 1 over x becomes 1 over x plus 1, right? 1 over x, we can flip and multiply again. I'll spare you the details. That simplifies to just x. And so our expression for g of 1 over x is x plus 1. And that's very convenient because now we have very simple expressions for both g of x and for g of 1 over x. And so we can put those together to finally show the end result that we were hoping to show all along. We can show that x times g of x times 1 over x plus 1 minus g of 1 over x, that is x plus 1, is equal to 0. And now showing that is not all that difficult. We're going to multiply through the brackets by the x. X times 1 over x is 1. X times 1 is x, and then minus x, also minus 1. And then you can see fairly easily that the x's cancel each other out, and the 1's likewise cancel each other out. And so we've managed to show algebraically that 0 is equal to 0. That is certainly the case. And so we've shown that for all values of x, except when the functions wouldn't be undefined, namely where x is 0, for all other values of x except 0, x times g of x minus g of 1 over x is equal to 0 always. And so I hope this helps. Again, this is simply an exercise in algebraic manipulations and using logarithm laws to simplify down certain expressions. But again, any problems like this simply requires you to go step by step, manipulate what you can algebraically, simplify your expressions down, and then put those expressions all together in the end to show your desired result. I hope this helps. And again, thanks for watching.